Today we're going to talk about approximating integrals, and we actually did some of this last year in Calc 1 when we started out integrating. So parts of this are going to look familiar. And in class, we'll talk about why in the world would we want to approximate integrals. We've just spent a long time talking about how to use different techniques to integrate functions. So why would we want to approximate integrals? And the quick answer is that we're not always actually going to be able to compute integrals by hand. There are some integrals that we just can't do by hand, so approximating integrals will give us a way to deal with that. And let's go ahead and jump in. This first one, we're looking at the region under this square root function on the interval from 0 to 2. We want to set up an integral that gives the area of this region. In order to set up an integral like this, we need to look at the region first and see whether it's above the x-axis or not. So let me pull that up on Desmos. So this is our function. We notice that it's not defined for all x because of that square root in there, and that's perfectly okay. Its domain is -2 to 2. We're only looking at the area from 0 to 2, so we're just looking at this right-hand side of the function. So let me go back and I'll draw that, and then we're going to set up that integral. So we've got this function. Well, it looked a little flatter than that, didn't it? Something like this. This is the area we're looking for. Since that's totally above the x-axis, the integral from 0 to 2 of this function will give us the area under that curve. Later in the semester, we're going to do more area problems. Okay, so it turns out that this is an integral that we cannot actually compute by hand, and not just me and y'all, all mathematicians. So you could try u substitution. This one, maybe you could try a trig substitution, except for the fact that this x over 2 is raised to the 4th power. It's not squared. So you could try some of the techniques that we've used already, and they're not going to work. So we're going to need to be able to approximate this integral. So if you remember last year when we started out finding area under curves, we did things like used rectangles, and that's what we're going to do to get started. So this first one says use left endpoints and 4 rectangles to approximate this integral. So we remember if we're going to use left endpoints, then I like to start out by just drawing, well, nah, I'll do it up here. No, I like to start out by drawing the number line from 0 to 2. We're going to have to break this into 4 equal pieces. So let's figure out how long each of those pieces are going to be. So we usually call that delta x is the width of each of the rectangles. So the length of our whole interval is 2 minus 0, which is just 2. And we're dividing by 4 rectangles. So each of these is going to be 1/2 wide, which you probably could have figured out without doing that calculation, but that calculation will work in general, even when we have messier numbers. So each rectangle is going to be 1/2 wide. So we're going to have increments like this. Okay, so we could put that on my original graph. We have a 1/2, a 1, and a 1.5, which is 3/2. Okay, so if we use left endpoints, remember that means that we pick the left endpoint of each interval to create my rectangle from. So I'm going to start, like, for instance, at 0. I'm going to go up to my graph and across and down. So that rectangle has height given by f of 0, okay, because we went up to the function there. And then my next rectangle, I'll go up to 1/2 over and down. So it has height f of 1/2. Notice I'm just putting the height of the rectangle right now. We'll deal with the width in a second. My next one is f of 1, and my last one is f of 1.5. We have to multiply all of these by the width of the rectangle, which was 1/2. That was our delta x. So what we're thinking here is we have height times width. That gives us the area of our rectangle. So if we plug all of these values into our original function, add them up and multiply by 1/2, we do some messy calculations on a calculator, we get 1.897 as our approximation for the area under this curve. Remember that this approximation would get better if we used more rectangles. And the exact area under the curve is what we get when we use infinitely many rectangles. Okay, so now maybe you should try getting this set up on your own using right endpoints. So we're actually going to have the same increments as we did before. We can have the same number line, and just copy it down here. The only thing that changes now is that we use the right endpoints instead of the left endpoints. So the endpoints that I'm going to use now are the 1/2 because that's the right of the interval from 0 to 1/2, the 1, the 1.5, and the 2. So when I draw those rectangles, I go up to 1/2, over and down, up to 1, over and down, up to 1.5, over and across. I should probably be saying over and across. And then at 2, that one just has height 0, so that's just kind of a non-existent little rectangle there. So again, we're going to multiply the width of each rectangle by their heights, which will be f of 1/2 plus f of 1 plus f of 1.5 plus f of 2. Okay, and if you do the math here on your calculator, hopefully we get correct that this is 1.397. Okay, we notice that this is an underestimate because all of these rectangles live under the curve. The previous one was an overestimate because those rectangles lived above the curve. So our actual estimate should live somewhere between 1.397 and 1.897. Okay. So we can use left endpoints, we can use right endpoints, but we can also use the midpoints of our intervals to approximate. So if we do that, then let's think about what's happening there. So we're going to have the same little number line that we're working with. So let's just copy that down here. But now instead of choosing our heights based on right endpoints or left points, what we're going to do is we're going to use the midpoint. So we have to look at the interval from 0 to 1/2 and ask what's the midpoint there? That's 1/4. Whoopsie. So 1/4. So the way that we're going to create that rectangle is we're going to go up at 1/4. This rectangle is still going to have width 1/2. So we're going to go across in both directions so that it goes all the way from 0 to 1/2. Okay. And then, so the height of that rectangle will be f of 1/4. Its width still will be 1/2. The width of all of these will still be 1/2. So we're going to still multiply by 1/2 on the outside of everything. Okay. My next little midpoint between 1/2 and 1 will be 3/4. So we're going to end up with an f of 3/4 because that rectangle, we're going to go up at 3/4 and create a little rectangle there. You notice that these rectangles are both kind of below the graph and above the graph. They include a little bit of extra on one side and a little bit less on one side. So it's not obvious whether these are over or under estimates. Okay. And then we're going to get 2 more little rectangles if I draw them here. Okay. And let's figure out what the middle points are going to be there. So halfway between 1 and 1.5 is 1.25. And then halfway between 1.5 and 2 is 1.75. So we're going to have plus f of 1.25 plus f of 1.75. Okay, and if we calculate that, we get 1.777. Okay, we notice that number is between the two numbers that we got above. That's probably kind of makes sense based on how we're creating these midpoints. Turns out that the midpoint estimate is usually better than the left or the right hand estimate. In class, we're going to learn something called the trapezoidal approximation, which is going to use trapezoids instead of rectangles. But before we do that, let's look at one more example here. So this one, we're not actually given a function, we're just given a table of values. So we're trying to estimate the integral from 0 to 5 using the midpoint rule. It didn't tell me how many rectangles, but if I'm going to use the midpoint rule, then it probably makes sense to look at 1 rectangle, 2 rectangle, 3 rectangles, because then I know information about the midpoints. Okay, so let's do this. So the width of each of these rectangles, in this case, the width from 2 to 3 is 1, from 3 to 4 is 1, from 4 to 5 is 1. So my width is 1 in each case. And then I need f of 2.5 plus f of 3.5 plus f of 4.5. So f of 2.5 is 3.1. F of 3.5 is 4.2, and then we have plus 3. Okay, so if we add all those numbers up, you should get 10.3. Okay, so lots of different ways to approximate integrals. Again, we'll talk in class about why we care about approximating integrals, and then we'll do some examples with rectangles and then talk about how to use trapezoids for approximating things.